Hey, welcome back to our second video on liquid nitrogen and phases of matter. We've got some more experiments to do showing you how liquid nitrogen can make things have different properties and going through the different phase changes. So we're going to be doing that. I want to remind you also we're going to have a follow-up Zoom to the first video and to the second video. If you got any questions about what we've been doing, hopefully we can find an answer for you there. And we'll do a few more experiments during that Zoom as well, some short ones, and we'll do a survey as well to try to see if you learn anything. So check the schedule for that stuff.
So in this series of experiments, we're going to talk a little bit about how different materials change their properties as they go from what we're used to at room temperature into the sub-freezing temperatures of negative 321 degrees of the liquid nitrogen. So pennies are kind of a fun example because in 1982 they changed from being solid copper to a zinc core with a copper coating. I'll let you Google why, see if you can figure that one out. But I think I have a 1980 there. And we're just going to throw these into the liquid nitrogen. 13. That one's a 78, so that one definitely ought to get. As Stacy moves the camera in close, you can see that the pennies are so hot that they are bubbling. They're boiling the liquid nitrogen. This would be like if we thought about taking something like a bolt or something that we'd heated up in the shop. Maybe we're cutting it off a piece of equipment and we throw it, we get it cut off, it's red hot, we throw it in a bucket of water and it just sits there and boils. That's the exact same thing that's happening here, just that the liquid nitrogen does it at such a low temperature. So while we're letting our pennies get down to a low temperature, we're gonna show what happens with those when we impact them with a hammer. Let's see what happens with some bouncy balls and some rubber balls. Go ahead and back up, Stacy, and we'll video some of this. But I have just a rubber ball that came from like the arcade. You can see it bounces, it's all normal. Let's drop it in here. I don't know if you can hear on the video, but it's boiling that liquid nitrogen just like we would expect, because it's 400 degrees different. I have a racquetball. I'm not sure what we really do with racquetballs, but they are a whole lot of fun to take underneath the cabinet and throw in there, and they go back and forth. But we got a bouncy, this racquetball, it's pretty bouncy. We're gonna drop it in there and let it do its thing. And then these are just regular, small, cheap bouncy balls, come out of like a quarter machine. So we're gonna drop those in there. And all of those are still so hot that they are boiling the liquid nitrogen out of there. So you see our pennies have gotten down to temperature. So I'm gonna let the bouncy balls do their thing. I'm gonna grab a penny. This looks like an old one, I'm not sure. We're gonna see. So, having trouble here. So that one definitely must be an old one, based on what it's doing, I think. Here's one of the newer ones. Oh, see what happened? It shattered and broke. All right, I want to make sure I get an old one. So you can see that the newer pennies with the zinc core get hard and brittle, and they don't take the impact well. An old penny with the copper core, this one is the 1980, I don't know if you can see it there or not, it just flattened out. So it took the impact, it didn't break. It remained kind of what we talk about with metal, it would be malleable. It's not a hard metal. There's some steels, like knives and stuff, they'll break before they bend. It's the exact same thing that's happening here, just at a really cold temperature. The zinc shatters, it doesn't bend. The copper just bends. Let's see what happened to our bouncy balls. They're probably down to a cold temperature at this point. We're gonna see if we can scoop. I wanna get the little rubber balls out first if I can. So we remember what they did last time. So we're gonna bounce them this time. They sound a whole lot more like a marble now than they did. They've lost that elastic property that they had. Oh, see ya. Can go away. Let's get the big one out, the big bouncy ball. Okay, so we remember what it sounded like. It sounds like almost like glass. Definitely lost the elastic properties that it had. And then the racquetball. Let's see what it does. So we remember what it bounced like, and it lost all of its elasticity in it. So what difference does some of this stuff make? Well, we know we're not ever going to do something technical probably with a bouncy ball, and that's not a huge deal. But if we're thinking about how we're going to build a part on a machine that maybe we're going to send into space for exploration or something, we know that the temperatures are going to be very low. Do we want to use a metal like zinc to put on maybe the landing gear, or do we want to use something that's more like copper that can absorb an impact without a structural failure? So all metals have different properties in different temperature ranges. That's why we select them to do different things. Just kind of an idea, just a way to show you. If you got any questions, follow us up on the Zoom.
All right, so we're going to try another experiment here with an ordinary empty water bottle. I'm going to crush it down here at the atmospheric pressure of about 14 to 15 psi. We're at here, right here in Muskogee, Oklahoma. And we're going to put it inside the vacuum, pull a vacuum on it, and see what happens. Do you have any predictions on what will happen and why it's happening? Well, they're expanded because there's less pressure pushing down on it. Even though we thought we'd already completely crushed it down, there was some pressure inside of it. And those atoms that were, there's the same number of atoms inside that bottle as when we had it all crushed up. There's just less pressure pushing down on the outside to hold them together, so they're expanding out, and each atom is taking up more room within that bottle. So now we're going to let off the vacuum, and what do you think will happen? So it goes back to normal atmospheric pressure, and that the atmosphere is crushing it down. And then we'll put the vacuum back on it, pull all the air out. There you have it. So here I've just got a regular balloon, just barely blown up, and here we're about 700 feet above sea level, right where we are here in Oklahoma, something like that. There's around 14 to 15 pounds per square inch on every square inch of us and this balloon from the atmosphere piled up upon us. So what do you think is going to happen if we put this in the vacuum chamber, and it won't have any pressure holding it together, and we'll see what happens there. So you can see the balloon's expanding. Why is it expanding? Because out here, outside the vacuum, it had the air, was all around it, holding it together. Now we're removing that pressure. There's the same number of atoms inside that balloon as when we first started. It's just that there's more space in between them now. They're expanded out. They're taking up more space per individual atom. And then when we release the vacuum, there'll be just the same amount of atoms inside the balloon. It's just that they'll have the atmospheric pressure holding them together. Now we'll go back the other way with vacuum, taking the atmospheric pressure off.
Quarter turn for greatness. I just turned it over because a while ago when it sucked it flat, it covered the vents in the bottom where it was sucking air out of. So I'm turning it over because I want it to suck. I want it to fill that whole chamber. Oh, my balloon.
That's even an example of how they use weather balloons. They'll air them up with helium here on Earth and let them go at roughly sea level or whatever. And then when they get to 50,000 feet or 80,000 feet, wherever they are, there's so little pressure up there that they expand out and they'll pop. All right, so now we're going to show you how again, different materials, elements change their properties when we change their temperature. We've got liquid nitrogen at negative 321 degrees is where it's a liquid. We can actually turn it into a solid if we can get it down to 346 degrees below zero. And like water will boil at sea level at 212 degrees, but at 15,000 feet above sea level, it'll boil at 184 degrees. So liquid nitrogen has those same properties. It's just within a different range of temperature. So we're going to pull a vacuum on this, and there's going to be less atmospheric pressure pushing down on the liquid nitrogen, and that's going to let it become a solid at a temperature that it wouldn't normally be a solid. So now we're going to put this in. We're going to put it in a vacuum.
As the liquid nitrogen is, the pressure around it lowers, it boils, continues to boil. Some of the liquid nitrogen is evaporating away and it's cooling what's left behind. This is the same thing that happens when you are outside and you are sweating. The liquid that's on your skin is evaporating away, and as that phase change occurs, a cooling effect happens and you're cooler. As the liquid nitrogen continues to boil, it's losing some heat through this evaporation process. It's getting cooler, and we're going to get down to that 346 degrees below zero that Rick talked about, and we should see some ice crystals form. They're not really ice, they're nitrogen crystals.
It's solid nitrogen instead of liquid nitrogen. And like the atoms that will vaporize and boil off, they are actually the hot ones. Like they're going to be a little below 300, negative 320, like 318, and so that's just going to leave back the coolest atoms are left in there, and those are going to start cooling the whole thing down. Hopefully we can pull a good enough vacuum on it to get it down to that negative 346. It's working. It's there right now. So there you see it. It kind of comes and goes. It's just very on the hairline getting warmed up. The solid forms, but there it kind of goes through there is the solid, and you can see it forms a crystal all at once. The atomic structure is actually changing within as it gets down and cools off. We've removed all the warmer atoms, and it's just these coldest atoms remaining down to negative 346 below zero in Fahrenheit. And so I'm going to shake it just a little bit, or just put my hand enough to warm it. And I thought that would change it, but it didn't. So it's pretty solid right there. Then we've got it under a vacuum, and it doesn't have any, and it's allowing it to cool off enough. We've removed all those warmest atoms and got it down to 346 for liquid nitrogen to become a solid. Now we're going to take the vacuum off. And as the vacuum kind of goes down, probably got a little small leak somewhere. Turn the valve and you see it goes back to the liquid under atmospheric pressure, which is about 15 pounds per square inch that we have here at the sea level we are.
All right, are we ready? In this experiment, we're going to talk a little bit about what happens to the air that we breathe every day when we supercool it. We're going to talk a little bit about kind of condensation, I guess is what this is really about. We've all seen condensation. The most time you think of it, imagine a drink on a hot summer day. It can be a can like this, and you'll have water droplets that are forming and flowing down the outside of the can, or maybe on a glass or something like that. In this case, we have the water vapor that's in the air is condensing and actually freezing above the liquid nitrogen line. You can see that line that's kind of dancing along right above the Coca-Cola. That's the level of liquid nitrogen that's inside this pop can. And anything below that line, what's being condensed out of the air is oxygen, like the oxygen that we're trying to breathe. Anything above that is I guess it is just the condensation coming out of the air, just the water vapor coming out of the air and freezing. You can really see a lot of it forming along the pop tab on the top. It's almost a snow that's condensing out of the air and forming. If we raise up on it, we can watch that liquid oxygen drip off of the outside of the can, and you can kind of see it on the screen of this iPhone. See if we can get it dripping. So it drips down, the droplets come down, and the screen of the iPhone is so hot because it's room temperature compared to the negative hundreds of degrees that we have in this liquid oxygen. I don't know what, that's a Google question for you. I don't know what the boiling point of oxygen is. You can look that one up on your own, but the screen is definitely over that. And it looks like dropping a water droplet down on a hot griddle. It's boiling away as soon as it hits it, just because of the heat that's in that screen that's sitting there. So we know we have this liquid dripping off of it, and I've told you it's oxygen. Let's see if we can prove that in some way. So I have some candles that are set up here, and we know to have a fire you need oxygen, you need heat, and you need a fuel source. So the candles, the fuel, they're already lit and they're burning, so we know that there's heat there, and there is oxygen in the room. Only in the 20% range, because most of the air that we breathe is nitrogen, but in a gaseous form, it's a nitrogen. So let's take this, drip some of this down on these candles, and let's see what happens. Okay, so now we have the same candle, but we placed it inside this jar, and it's burning. It's kind of staying in there, kind of barely holding its own. We're gonna throw a lid on it. We have a hole in the lid, and we'll see what happens. So the flame's starting to get a little smaller. We're gonna take our can. We're gonna see about dripping some of that oxygen down inside the can. You can definitely see when the drips get in there that the candle kind of gets more back to what we call normal. Okay, we got a good amount of oxygen in there. You can kind of still see that there's liquid oxygen coming off, but it's coming down the side. So it burned enough oxygen out of the jar that it went out. We put some back in it. And when we put a fire back in there, we burned all the oxygen out in a hurry. Well, I hope you enjoyed our series of short experiments today. Again, my name is David Adams. I work for Parks and Recreation Department in the city of Muskogee. I manage the building that we use today, Hatbox Event Center. If you're interested in a location for a building in Northeast Oklahoma, we can host anything from a shooting sports contest to a livestock show. Just glad to have been able to come in today and hang out with my friends and show you some science.
We thank you for coming. Don't forget to join your Zoom. Make sure you're checking your email to watch for those Zoom links.
Yeah, thanks for coming. We appreciate it. Hope you enjoyed it. Freezing, blowing stuff up, seeing phase change. Normally we do this when we do this live. We have food to eat at the end, but since you guys aren't here, I guess we're gonna have to eat all the food. So, cheese puffs for everyone. Thanks for watching.